between the multiple model and the simple model. In the multiple linear regression model, we have more than one exponential variable. Remember that in the simple regression model, we had only one exponential variable. For example, in the wage equation, we have the only one exponential variable, which is the years of education, okay? But there are many other variables other than the years of education, which affect the wage rate of workers, okay? So we will have the more exponential variable in chapter 3. And when you have the more than two variable, we call that is the multiple. And still we are talking about the linear model. So the multiple linear regression model, okay? So in this case, we want to explain the variation in Y, for example, the variation in wage rate in terms of exponential variable x1, x2. Previously, we had only one variable, years of education, okay? In here, we have more than one. For example, x1, years of education, and x2, years of work experience, and so on, okay? So again, here's some definition of the variable. The variable y on the left side of equation, we call this is the dependent variable or explained variable. We want to explain the variation in y. And here the y depends on the x1 and x2. So we call y dependent variable. And most of the time, the y, the variable on the left hand side, we call dependent variable. Okay, most of the time we call y dependent variable. Okay. On the right hand side, we have the exponential variable x. Okay, and here we have the x1 and x2 and so on, xk. Okay, and this x variable we call independent variable. Okay, or we call exponential variable, or sometimes we call regressor. We call the variable x a regressor. Okay. Okay, so now in here, most of the time we call x independent or exponential variable, all right? Then here, the last term is the error term or disturbance term and unobservable. And this one, all other factors which cannot be observed. All other factors which cannot be observed. So that's why we call unobservable. But the factor error term also influence the y, okay? So there are factors like the exponential variable which influence y, and there are unobservable factor u which influence y, okay? So those are the factors x, u, y, okay? Then there are parameter, and the beta not, this is the without x, that's we call the intercept. And the beta 1, this is the slope parameter of the variable x1, and beta 2 is the slope parameter of x2, and so on, okay? So we have the variable, dependent variable error term, and we have the parameters. Now, you may ask why we do multiple regression. Okay, there are some important reasons. Okay, when you do a multiple regression, you can incorporate more exponential factors, okay, into the model, okay. Previously, we had only one factor, years of education, but we don't think that the uh, years of education can explain all of the variation in ways that is not realistic. However, when you have the multiple regression, you can have more variable, other variable. Okay, you can incorporate the more factors so we can better explain. And second reason why we do this, we can explicitly hold fixed other factors that otherwise would be in error term. Okay. In the previous chapters, for example, in the wage equation, we had only one exponential variable, years of education. And the other variable, for example, job experience, is contained in error term. Okay. Now, when you have the multiple regression, you can take out this job experience from the error term. That could otherwise would be error term, but now you can take out that variable from the error term. And by taking out and you run the regression, then you can interpret the slope parameter. In that case, the slope parameter represents the effects of the particular variable while holding the fix the other variables. So in other words, suppose that you have the two exponential variables, so you have the beta 1 hat and beta 2 hat to estimate, okay? Then the estimate of beta 1 represent the effect of the first variable, which is the years of education, while holding the effects of second variable, which is the job experience fixed. Okay, so that is the second reason why we do multiple regression, and I will talk about this more later on. Okay, so this is the very important. Okay, by doing multiple regression, you can hold fixed the effects of other factors. Okay, and the third reason is we can allow for more flexible functional form. Even though we have a linear model, by having a multiple regression, we can allow for more flexible functional form. Okay, I will show you later. Okay, this one. Okay, so let's let's uh, let's explain these three motivations, the motivation more carefully using example. Okay, so here we have the wage equation. So in this case, we have two exponential variable. Okay, so we want to explain the variation in wage rate of workers using a two exponential variable. First one is the work years of education, and the second variable is the labor market experience. Okay, job experience. Okay, and again, the error term contain all other factors. Okay, now Suppose that you run this multiple regression model and you estimate the slope parameter beta 1, okay? And this beta 1 now measure effective education, explicitly holding experience fixed. We hold the this factor experience fixed, okay? So the beta 1 measure effects of education explicitly holding job experience fixed. Suppose that you learn the simple regression, okay, wage, beta not, beta 1 education and add them without this one, okay. In that case, this beta 1 may also reflect the effects of job experience if the education years education and job experience are correlate. So, so in order to avoid that possibility, okay, we want to truly estimate the true effect of education on wage rate. You run the multiple regression, okay? So that's what we can do when you can explicitly hold fixed other factors, okay? Okay, this example give you a clear idea of that point, okay? Okay, let's do, okay, here. Dependent variable is the average standardized test score of school, okay? And we think that this average standard score depends on per student spending at the school expenditure and also depends on the average family income of student at the school and the little u or other factors, okay? Now here's it's more likely that per student spending, the first exponential variable is likely to correlate with the average family income at a given high school because of school financing, okay? When you have the higher average family income at that high school, you'll have a greater school financing, so you'll have a greater per student spending or so. This per student spending more likely to be correlated with the family income, okay? Now, suppose that you run the regression, and in this case, you omit average family income in regression. So you run a simple regression model. Okay, so wage, beta naught plus beta 1 expenditure and the other term. Okay, without the second term. Okay, suppose to do that. And you estimate the beta 1. And then you estimate beta 1 will lead to bias. Bias, this is key. Okay, this is a bias estimate of the effect of spending on average test score. Okay, well, this is the point. Okay, suppose that you run the regression without the second variable, and you estimate the beta 1. Now the expenditure, in that case, the expenditure. Suppose that you run the regression without family income. So maybe this family income may be contained in the error term, okay? In that case, the expenditure and the error term is correlated. And you estimate the beta 1. What does beta 1 measure? That measures the effect of spending on score. But in that case, the spending and the error term, which contained family income, are correlated. Okay, so that beta one, that effect, when you omit, that will have the biased effect, because that one captures also the effect of family income, which is contained the error term. Okay, so in a simple regression model, okay, so without the average income, in that case, the average income is in the error term. Okay, the effects of post-student spending would be partly, in that case, beta one, partly include the effects of the family income on test score. Okay, so this is the point. Okay, so I will repeat. Suppose that you run the regression without this average income variable. Okay, so in other words, this average income variable in the error term. In other words, you omit the average family income. Okay, so you have a simple regression model. In that case, the effects of post-student spending, the beta one, would partly include the effects of family income on test score, because it's more likely that the post-student spending correlate with the average family income. Okay, so in other words, higher post spending, you tend to have higher average score, but you tend to have higher average score not only because the higher post spending, but also what? Because higher family income. So in that case, the beta one reflect the effects of post spending, but also the effects of the family income. So in other words, the beta one is supposed to reflect the true effect of only the spending, but it also pick up the effect of family income. So that estimate bias. So in that case, how we can solve, this kind of the problem in such a case? In that case, you can take out the average income from the error term. So you have a two explanatory variable. When you take out this variable and regress on two variable, expenditure and average income, and you estimate the beta one, the slope of spending. In that case, this effect reflect the effect of the expenditure only, while we're holding average income fixed. Okay, so that's why it means by in here. Okay, so that's you can, when you have a multiple regression model, you can explicitly hold fixed. You can explicitly hold fixed other factor that otherwise would be in error term. Okay, so when you run the multiple regression and you estimate this beta one, okay, in that case, you can, by running multiple regression, you can hold this second variable fixed. In that case, this estimate reflects the effect of the change in only spending. Okay, so that's why we are running multiple regression. Okay, that is the point. Okay, so this is the very important point. All right, why we run the multiple regression? Because we can explicitly hold fixed other factor that would be contained in the other term, okay? The third motivation is we can allow for more flexible functional form. That's what it's saying here. We said we can allow for more flexible functional form. Okay, so let's explain this. Okay, so this is the example, okay? So here the dependent variable is the family consumption, and family consumption depends on the family income. Obviously, higher income, the family with higher income spend more, right? But here we have the another variable, family income squared. When you have the simple regression, you can have the only this variable, income variable. But when you have the multiple regression, you can have this family income square variable. You can have the second variable, okay? So by having this family income square variable, this is what? Quadratic function, okay? So consumption is the quadratic function of the family income, okay? So you can allow for more flexible functional form, okay? This is the quadratic functional form, okay? So you have the two exponential variable, income and income squared. So we can allow for more flexible functional form. In other words, the consumption is the quadratic function of income, okay? Quadratic function of income. Now, you may wonder that, say that we are talking about the linear model, but in this case, we are saying that the linear in the parameter, okay, linear in beta naught and beta 1 and beta 2. We are not saying that the linear in income, okay? So still we are talking about the linear model, but we can allow for the more flexible functional form, okay? So suppose that you run this regression, okay? So you estimate the beta 1 and beta 2, okay? So in this case, how much consumption change when income change? Okay, so that is this one, okay? So you take the derivative of consumption with respect to income, then you come up with that the beta 1 and 2, beta 2 income, okay? So what it says, how much consumption increase if income increased by 1 unit, okay? And this says how much consumption increase depends on how much income is already there. So what it says is we have two family, a lower income family and the higher income family. When income increased by 1 unit for each, suppose that the lower family income increased by $100 and higher income family increased by 100. If you think that the consumption will increase by the same amount, lower income increase consumption by 80 and the higher income increase consumption by 80 same amount, usually economic study tells you that lower income family spend more when they have a increase in income, spend more than high income family. Maybe a low income family spend 90 when income increase 100, and higher income families spend like the 70 when income increase 100. Okay, so in other words, that we call the marginal propensity to consume. This is what we call the marginal propensity to consume, depends on income level. Okay, so usually marginal propensity to consume of the lower income family is higher than the marginal propensity to consume of the higher income family. In other words, it says this marginal propensity to consume depends on the whether the family is higher income family or the lower income family. Okay, so by allowing for this quadratic function of income, we can capture this point. Okay, so that's why we run the multiple regression. When you run the multiple regression, we can have the more flexible functional form. Okay, another example is that log of salary depends on the log of sales, and here this is the CEO tenure with the firm. How long CEO work with firm, okay? And this log of salary is the quadratic function of the CEO tenure with the firm, okay? So this is more flexible functional form, okay? Salary depends on sales and CEO tenure, and also salary is the quadratic function of the CEO tenure, okay? In here, you have the log of sales and a log of salary and log of sales. So the model assume a constant elasticity relationship between CEO salary and the sales of his or her firm, okay? So the beta one measure the change in log of salary in response to the change in log of sales. Okay, so that is change in log, always we say the percentage change. So change in low salary is the percentage change in salary, and change in low sales is percentage change in sales. So beta one measure when sales increase by 1%, how much percent the salary CEO increase. Okay, so that is the we have the log. Okay, remember that the log change in log percentage change, and also model assume a quadratic relationship between CEO salary and his and tenure with the firm. When you have the CEO salary, it means that the percentage change in salary also depends on the how long CEO has been working with the firm. Okay, here the meaning of linear model, we are talking about the linear regression. Okay, so we are saying the linear means the model linear in the parameter, not in the variable. Okay, when you say linear, it means that uh, linear in parameter, linear in beta naught and beta 1 and beta 2, beta 3. Okay, now then how we find the OLS estimation. how we find the OLS estimator of the multiple regression model. Okay, so this is the very similar to what we done before in the case of the simple regression model. Okay. Again, you draw a random sample. Okay, so you have the n observation. And so you run the regression and you calculate. Suppose you calculate the residual. Okay, you had is the residual. This is the difference from the u without had. That's the error term. Okay, residual with had is the difference between actual yi and the predicted y hat. And predicted y hat is this from this fitted regression. Okay, so this is the fitted regression. Fitted regression give you fitted value of the y, which is y hat. And the u hat is the difference between yi and yi hat, and that is the fitted yi, and fitted yi is determined by this fitted regression. Okay, so you have this estimate. Now, again, we want to find this slope parameter such that we minimize the sum of squared residual. Okay, and how you minimize, computer will do for yourself. And so suppose that you have the slope parameter. Okay, what's the meaning of slope parameter? Slope parameter tells you by how much does the dependent variable y change if j's independent variable, for example, the first variable could be education, is increased by 1 unit. Here the point is holding all other independent variable and the error term constant. Okay, so the meaning of the slope parameter in the multiple regression tells you how much y dependent variable change when j's exponential variable change by 1 unit. But in this case, this is the partial derivative, so we are holding all other variable, all other exponential variable and error term constant. Okay. So by running the multiple regression model, the multiple regression model managed to hold the value of the all other exponential variable fixed. Maybe even if in reality they maybe correlate with the exponential variable under consideration, but here when you run the multiple regression, what you're saying is that we hold all other variable fixed. It means we have ceteris paribus interpretation. Okay, it means that we are talking about the change in y when we have only the change in particular explanatory variable while holding all other variable fixed. And that is what mean by ceteris paribus interpretation. Actually, ceteris paribus is a Greek word. And also at the same time, it has to be assumed that error term do not change even if the explanatory variable are changed. Okay. So let's walk with example. Okay, here we are talking about the determinants of college GPA. Student college GPA, the grade point average, depends on his or her high school grade point average. Okay, so this is high school grade point average, and also depends on his or her achievement test score. Okay, and you draw the random sample. Okay, and you run the multiple regression, and you estimate. We talk about how you compute the slope parameter. The computer will print out the estimate beta naught hat and beta 1 hat and beta 2 hats. Then how we do interpret these numbers. Okay. So how we interpret this number, 0.453, how we interpret it. What this number tells you, 0.453. This number tells you that holding other variables fixed, in other words, ACT fixed. Another point on high school GPA we associate with another 0.453 points college grade point average. Okay. In other words, equivalently, or if we compare two students with the same SAT, okay, same SAT, but the high school GPA of student A is 1 point higher than the high school GPA of student B. Then we predict that student A to have a college GPA that is 0.453 higher than the college GPA of student B. Okay. So the first statement and the second statement are actually the same. The first statement, we are saying that we hold ACT variable fixed, and we only have we have only another point on high school graduate. Hold this one fixed, and we have another point on high school GPA. Then we predict that the GPA, college GPA, will increase by 0.45. The second statement says, suppose that we have the two students and two student SAT are the same. In other words, we are holding SAT variable fixed, constant, okay, for two students. And student A high school GPA is higher than the student B high school GPA by 1 point. In that case, we predict that student A college GPA will be higher by how much? 0.453 than the college GPA of student B, okay? That's what we mean by holding other variable the fixed, okay? We can apply the same interpretation to the second variable, okay? So what does this number mean? 0.9, 0.0094 SAT. Think about it. What this number mean? We talk about what this number means, okay? Now you think about what this number, the slope parameter, what this number mean associated with SAT. Think about, I'll give you 5 minutes, okay? Think about it. Okay, you think about that, okay? Now, this means that the number 0.0094 means that in this case, we are holding the other variable. In this case, other variable is the high school GPA. High school GPA fixed, okay? Then another 10 point on SAT associated with less than 1 point on the college GPA, okay? So you have the 10 point. So 10 times 0.0094 will be 0.094, okay? When ACT higher by 10 points, how much college GPA high, okay? So you multiply this number by 10. So if you multiply 0.0094 by 10, then you come up with the 0.094. So 0.094 is that the less than 1 point or less than 1/10 of point. 0.094. 0.094 is less than 1 point or less than 1/10 of point. That is less than 1/10 of point. Okay, so I think this is the type. Okay, less than 1/10 of paper, 1/10 of paper, 1/10 point, 1/10 point, 1/10 point. Okay. Okay, I think this is the way I stop in this chapters, and we have some some time to go. So let me find some exercise for you. Okay, wait a minute.
여보 몇 시에 끝나?
응?
몇 시에 끝나?
뭐?
몇 시에 끝나?
조금 이따 끝나.
2시까지 가기로 했는데 어떡하지?
Okay, I have the one multiple choice problem for you here. Which of the following can cause OLS estimator to be biased? A. Heteroscedasticity. B. Omitting an important variable which is correlate with a independent variable. 3. A sample correlation coefficient of 0.95 between two independent variables, both include in the model. Okay, so which one cause biased estimate? Okay, I'll give the 10 minutes. Okay, I'll give think about it. We studied this, and I'll give time. Okay.
벌써 여보?
아니, 문제 풀라고 준 거야.
얼마나 기다려?
5분 후에 다시 시작해.
그러니까 다 언제 끝나냐고.
5분에 다시 끝내.
그냥 아니면 2시까지 간다 그랬거든? 위례?
응?
위례 2시까지 간다 그랬거든.
지금 2시 안 되지. 4시 50분 했거든.
그러면은
전화해, 그럼 좀 늦는다. 밥도 못 먹겠네.
다른 집 가서 먹어도 돼.
응. 전화해야지.
장관한 거 천천히 먹어.
가만 근데 옷을
옷?
꺼내라, 옷 갈아입.
노트북 가져가야지.
응. 오늘 거기서 잘 거야, 아니면 올 거야?
와야지. 상식이 어딨어. 바로 코앞인데 뭐하러 저녁에 남의 집에. 강아지 데리고 산보 갈 거잖아.
그걸 이러고 할 수 없잖아.
그러니까 얘랑 이렇게 입어.
응?
얘랑 이렇게 입으라고. 얘랑 바지도 내복도 하나 입고. 하도 추위를 타니까.
Okay, you think about this problem. Okay, let me go over the problem for you. Which of the following can cause Euler's estimator to be biased? Okay, first one, heteroscedasticity. What is heteroscedasticity? It means that the variance of the atom is related to the explanatory variable, okay? And when we have this kind of the problem, it will affect the variance of the slope parameter, variance of the beta 1 hat. So it has nothing to do with the bias, okay? So later chapter, so we will talk about the problem with the heteroscedasticity. Okay, this is something to do with the standard error of the slope parameter. Okay. 2, omitting an important variable which is correlate with an independent variable. Okay, so the correct answer is 2. When you omit an important variable, in other words, you have this variable in the error term, so that error term is correlate with the independent variable, your estimate of slope parameter will be biased. Okay, so go back to previous example that the test score that depends on per student spending and the average family income. We talk about that. Okay, so suppose that we omit the family income variable. And the family income variable is correlate with the independent variable, the post-student spending. And then you estimate the effects of post-student spending on this test score. And we know that post-student spending is correlated with the family income. In that case, the estimate of the slope parameter will be biased because the estimate reflects not only the effects of the post-student spending, but also the effects of the family income. In other words, your estimate will be overestimate, meaning biased, overestimate, meaning biased. Okay, so number 2 is the correct answer. 3, sample correlation coefficient of the 0.95. Okay, so correlation lie between 1 and -1, and 0.95 is very highly correlate between two independent variables. When you have the independent variable which are highly correlate to each other, you have so-called multi-collinearity problem. We'll talk about later chapters. When you have the multi-collinearity problem, the standard error of the coefficient will be affected. Okay, so number 1 and number 2 something to do with the standard error of the coefficient. Number 2, something to do with the bias. Okay, so the correct answer is number 2. Okay, so all right, so much for the today class, and you'll have 2 weeks off for a lunar holiday, and I hope that you have a good time with your family at home. I'm having a good time here in Seoul, Korea. Okay, talk to you later. Talk to you 2 weeks later. Okay, all right. If do you have any question? Okay, if you do not have question, then I will stop class. Okay, bye. Okay, bye, everybody.
Happy New Year.
See you. Not see you. Okay, talk to you 2 weeks later. We'll have an online class 2 weeks later. Okay, have a good time.